I got a few requests to do number 2B from the hemoglobin practice problems. In week 8. And I'll do another video for 2C because that was requested as well. But all sections of this problem have to do with the acid-base properties of oxy and deoxyhemoglobin. And you're given some reactions. For oxyhemoglobin at a particular residue, there's protonation, and that proton can come off that residue. And that reaction is described with a pKa of 6.2. And then for deoxyhemoglobin, we're also looking at a single residue where you have protonation, and that comes off in a characteristic way described by its pKa, which is 7.7. So different pKa's for the deoxy and oxyhemoglobin. And so in 2B, you're told that a student is making a 1 liter solution of 2 millimolar hemoglobin, and it's at pH 7.4. And the oxygen saturation is 80%. So this problem combines hemoglobin, an understanding of hemoglobin, with an understanding of how to use Henderson-Hasselbalch. So to do this problem, the question is then saying, please calculate all the forms of hemoglobin present at this pH. And the problem nicely lists out what the forms are. So a deprotonated deoxy, protonated deoxy. You also have a deprotonated oxy and a protonated oxy. So these two are the deoxy forms, and these two are the oxy forms. One protonated and one deprotonated for each form. So to figure out how much of each you have to do Henderson-Hasselbalch for this pair, and then you have to do another Henderson-Hasselbalch for this pair, because the pKa will be different. For the deoxy pair, the pKa that you're going to be looking at is 7.7. And for the oxy pair, the pKa that you're going to be looking at and using is 6.2. So you're told the total molarity is 2 millimolar, but how much of each do you have? So if you're 80% saturated with oxygen, that means your total oxyform is 0.6 millimolar. So that gives you the total concentration for the two forms of oxyhemoglobin. So we can now do Henderson-Hasselbalch for the oxy versions, and we'll set that up. So we know pH equals pKa plus log of A minus over HA. So our A minus is the deprotonated form. Our HA is the protonated form. The pH of our solution is 7.4. The pKa of the oxy hemoglobin residue that's getting protonated or deprotonated is 6.2. And then I'll just rewrite the A minus over HA species. When you subtract 6.2 from 7.4 and take the antilog, you get 15.8. It represents the ratio of these two concentrations. I should have put my concentration brackets here, but you know what I'm talking about. So at this point, it's a regular old Henderson-Hasselbalch problem. There's two mathematical ways that I went through going from here to get to your answer. I'll cross multiply in this case. You pick whichever one that works for you. I mean, they both will work for you. Pick whichever one that makes more sense to you conceptually. So I'm cross multiplying here. And what that does is that gives us a nice equivalence to do an algebraic substitution. We know that the protonated form and the deprotonated form have to add up to 1.6 millimolar. So we do a substitution into that equation so that we go down to just having one unknown. And we put HHBO2 plus, and another way of writing HBO2 is 15.8 times HHBO2 equals 1.6 millimolar. This is 16.8 of our unknown, which is the protonated form. And this allows us to calculate the protonated form of oxy to be equal to 0.1. It's actually 0.09, but I'm rounding up. And I always tell you on exams what to report your final answer to. I'll say 1 or 2 digits, and usually I will pick something that matches the actual sig figs. But as I mentioned in this class, I'm not testing you on your memory of sig figs. So to calculate the deprotonated concentration, there's I think the easiest way to go about it is to say 1.6 millimolar is the total. You know the other version's 0.1, and so you're left with 1.5 millimolar as your answer for the deprotonated oxy. So those are the two oxy forms, protonated and deprotonated. You do the same exact thing to do the deoxy forms. The only difference is that the pKa that you use for the deoxy forms is going to be different. It's going to be 7.7 for the deoxy. And then the deoxy forms also add up to 0.4 millimolar. And there's a couple of ways that you would come up with that number. I think the simplest is to acknowledge the total was 2 millimolar of all of the forms of hemoglobin. You calculated that 1.6 millimolar was the oxy form. So the rest is going to be your deoxy form. In the solutions, the way they do it is that they say, oh, it's 20% of the total, which is also totally valid because you know it's 80% oxygen saturated. So it's 20% deoxy. I hope this clears up. If you have any further questions, please post on Piazza.